Well, you know, I should say that it's a great pleasure to give this talk, and thank you very much for inviting me. It's very unfortunate that I can't come. Just, you know, it just happened like this. So, Philippe, I wish you a very happy birthday. You know, in Chinese tradition, people live to 120 years. So first 60 years, you go up. Second 60 years, you go slow, you go down. So I hope you will keep up with the great tradition. And let me start. So, so here's the plan. So I'll talk about hybrid quantum systems, which is nothing new. It's a quantum system on a classical background. So I'll focus on hybrid integrable systems. And the main example is spin Kaluza-Moser system that's kind of, and this hybrid version will produce some kind of dynamical version of Haldane-Shastri model. So the talk is based on the joint work with Andrei Lashek and Ivan Sechin. So, you know, I'm so happy that, you know, in science, it doesn't matter whether you're from Russia or from Ukraine or from anywhere else. We're still happy to talk to each other. At least, let me hope. So our collaboration is an example of this. So quantum systems on classical background. It's well known in physics. It's basically what I'm talking about is, in physics terms, it's Born-Oppenheimer approximation when you have a classical, when you describe the, say, the nucleus as classical system and the electrons as quantum system. And the nucleus, they move independently of quantum system according to the laws of classical mechanics, and electrons, so they are spinning around according to the laws of quantum mechanics, but it's a non-stationary dynamical system because, you know, unless the atoms are fixed. So, I mean, you know, this is something of a dream of modern scientists, quantum computers. So when they will be available to use, so then of course there will be quantum classical interface. So part of this quantum computer will be quantum, part of it will be classical. So it's very relevant. Probably it's very dangerous because the State Department is blocking certain areas of research in other countries. So anyway, doesn't matter. So so for us, M is a symplectic manifold, and so what we want to construct is a quantum system which is driven by a classical system. So first, let's focus on the geometry of such things. So the geometry is the following. So we have a classical phase space, M, and then over each point of the classical phase space, we have the quantum algebra of observables. The simplest case is, you know, something that's relevant again for these quantum information games. So it's when over each point of the phase space, you have a finite dimensional algebra with star involution. So algebra of Hermitian finite dimensional operators. These algebras are different over different points of the phase space, but of course we want to identify them. In order to identify them, we have to have a connection that identifies different fibers, and that's an assumption. So basically, geometrically what we have is a symplectic manifold. on the symplectic manifold, we have the bundle of finite dimensional algebras with the star involution. And so the algebra of hybrid observables is just the algebra of sections of this bundle. So in other words, to each point on the phase space, we assign so an element of this algebra is a section which assigns to each point an operator acting in the algebra over this point. So we have a natural pointwise multiplication. So far, everything is trivial. So we have the star involution. So just the old story of foundations of quantum mechanics, but now the foundations are packaged in a different way. So then we have a center of this algebra, which is just the algebra of functions on M, complexified, and I is the unit section. So for each X, it assigns the identity in the corresponding fiber. So the center has a natural Poisson structure because we have a symplectic structure on M on the phase space. So, and the algebra itself is a module over the center. So we can take a section, we can multiply it by any function on M. We still have a section. So we want to have a module structure over the Poisson algebra on the center. For this, we have to define the brackets between sections and functions. So to do this, we need a connection, and here nabla alpha is the covariant derivative with respect to this connection. And once we have a connection, we have this Poisson bracket, and this Poisson bracket should satisfy these identities. So, and it does if you have a connection. So then a hybrid quantum system, kind of, here's the definition. I gave the motivation. It's a bundle of algebras over a symplectic manifold with the star structure and a Hermitian connection on it. Okay, so physical word for this is quantum systems on a classical background. Mathematical word is Poisson-Azumaya algebras. So Azumaya algebras, well, basically, since time is short, we can skip this. So then, what are representations of this quantum algebra of observables? So over each point of the phase space, we have to have a representation of the algebra AX. So this is what we have. And so this is what representation is. It's a vector bundle over M such that each fiber is a representation of the fiber of our bundle of quantum observables. And hello? Can you hear me?
Yeah, it's okay. Keep going.
Oh, okay, good. So, it's all compatible with the star structure. So there is a Hermitian structure on these representations, and we assume that this bundle is equipped. This vector bundle is equipped with connection beta, and this connection beta is compatible with our connection alpha in this way. So if you take the covariant derivative of AF, we have the Leibniz rule. It's equal to the covariant derivative of A plus the A times the covariant derivative of F. And so a remark that Poisson algebra, which is the center of our algebra of observables, is also represented in a sense in this way. Okay, so this is a kind of funny construction because we have our algebra acting on the sections on this vector bundle, and this vector bundle is over the symplectic manifold. In other words, it's over the phase space. So we certainly would prefer to have a bundle only over Q, so that our wave functions would depend on Q, not on P and Q. So for this, there is another notion of Lagrangian modules. So geometrically, again, it's a simple construction. So we choose a Lagrangian fibration. So Lagrangian fibration can be used for for humane purposes in the following way. First way is as an integrable system. It's a Lagrangian fibration over some base, n-dimensional base M. So it defines functions on B pulled back to M. They define Poisson commuting integrals. And the second typical use is geometric quantization. So we can construct vector spaces on which quantum algebras of observables act. So here is a third way to use it. So assume that we have such thing. So then assume that we also have a Lagrangian section. In other words, it's a Lagrangian submanifold in M such that it intersects every Lagrangian fiber once. So it's something like this. These are our Lagrangian fibers, and this is the section. So then we can define a new vector bundle, the vector bundle over B. That one. And it's exactly implementing our idea over here. So the fiber over point B is just our old friend fiber Vx, but over the point of intersection with our section L. So this bundle depends both on our Lagrangian fibration and on the choice of section. And then we can define the vector space, space of sections over B, and it's a so naturally functions act on this vector space. If you have a section of this vector bundle, and the function acts on this section by multiplication, and any element of A acts in the same way. It's just following. But Poisson structure is not represented there. It's these are kind of vector valued functions of Q, if you want. So now, what is the dynamics, hybrid dynamics? If we have a Hamiltonian, which is a function on our phase space, so the Hamiltonian dynamics generated by H0 on classical observables can be lifted to A using here we use the connection alpha, and then we can twist this lift by the choice of quantum Hamiltonians. In other words, we choose a section of our bundle of quantum observables, the Hamiltonian H1, the quantum correction, and we say that now the dynamics is the following. So here we use the connection alpha to lift the classical dynamics of H0 to the bundle. And here we twist these dynamics by H1. So then that's the Heisenberg picture. So the Schrödinger picture is the following. We take the section of our vector bundle, the representation bundle of A, and we say that, okay, the dynamics now is the following. So because our V is over M, So again, we can use the connection beta to lift the classical dynamics to sections of this vector bundle, but then we can twist it with the quantum Hamiltonian H1. And then we can get rid of this classical part simply by sort of doing something like a method of characteristics. So we will say that let's consider sections of our vector bundle along the classical trajectories. So in other words, let's consider these objects. So then the quantum dynamics is very simple. It's the usual non-stationary Schrödinger equation with the quantum Hamiltonians H1, but along the classical trajectory that's generated by H0. Actually, this system has a semi-classical limit, and it's a kind of double Hamiltonian dynamics. So there is a semi-classical limit. I don't want to talk about it now. It's just, it will be, there is not enough time. So then this dynamics on V can be, it also generates the dynamics on our Hilbert space of sections of the bundle V LB over B. So vector valued functions of Q. So that's the kind of Schrödinger picture in this dynamics. And then, geometrically, it has a natural geometric meaning. So, I will refer to the details. For the details, you can just look at our paper with Leszek and Sechin. So now let's go to hybrid integrable systems. So a classical integrable system, again, I already said this, it's Lagrangian fibration, which means that generic fiber is Lagrangian. There are singular fibers. So for example, this is a singular fiber, and this is a generic fiber for the harmonic oscillator. And typically in mathematical physics, we consider only generic fibers, but singular fibers are also very important, and of course there is a big science about them. So we consider typically classical integrable system is given by n independent Poisson commuting Hamiltonians, and the fibration is simply given by level surfaces of these Hamiltonians. So then, once you have an integrable system, unless there are some physical reasons to choose one specific Hamiltonians, you don't have a specific Hamiltonian. You have multi-time evolution, and integrable systems should be treated as such. These are systems with multi-time evolution, and this multi-time evolution given by the system of differential equations. So if you have a hybrid system, and if you have an integrable classical system on the phase space, you can lift these Hamiltonians to this bundle of quantum observables, and then you can twist them with quantum Hamiltonians. And so here's what you have. For each time, you have a hybrid evolution, which is the lifting of the classical integrable system twisted by the quantum Hamiltonians. Of course, it requires some compatibility condition. So in this case, the compatibility condition is the following. If you take the commutator of two quantum Hamiltonians, now it's not going to be zero. It's going to be the sum of these Poisson brackets plus this funny term that is, so F alpha is the curvature of the connection alpha. So if you look at the Schrödinger picture, it's the same. So here's the compatibility for the Schrödinger picture. Again, I'm sorry, I'm rushing through the talk because I have only 10 minutes left. So compatibility condition now is very interesting. It's not the commutativity of integrals, of Hamiltonians, quantum Hamiltonians, but it's the following. If you compute them along the multi-time trajectory, which means that you compute them on the Liouville tori, where these multi-times are local coordinates, then it's actually a flat connection on each Liouville torus, at least on each generic Liouville torus where they're independent. So what happens on special Liouville tori, low-dimensional Liouville tori, we will see in an example. So then it turns out that it's very naturally related to deformation quantization. So, for example, typical deformation quantization problem is you have a Poisson algebra and then you want to deform it into a family of associative algebras. So the only difference with this picture is that now A0, this is the H equals 0 case. This is the associative algebra of sections of our hybrid bundle. And the center is exactly the Poisson algebra that sort of we started, that we normally would have. So if you will do all the mantra about deformation quantization, we will see that the first jet of the deformation gives the Poisson structure, and then the same formula when Z is the central element gives the action of the center by derivations on A0, and geometrically it's exactly this connection that we have. And if we have a quantum integrable system in this deformation family, then when H is 0, so the first term gives the Poisson commutativity of H0 Hamiltonians. And I assume that quantum Hamiltonians have this form. So as H goes to 0, we have a classical Hamiltonian times the identity element in this algebra A0 plus quantum corrections. So in this case, H0 Poisson commute and H1, they satisfy this identity where bracket 2 is given by the second coefficients of the deformation. So anyway, so the conclusion is that there is such structures, the hybrid quantum classical systems. Basically, it's a kind of mathematical version of Born-Oppenheimer approximation. And here's an example. So let's consider the quantum spin-Kalodge-Moser system. So there is a prehistory that goes back to Cherednik-Dankov operators. And then if we will do it, then eventually we will have the, kind of after certain manipulations, we will have quantum Hamiltonians of a kind of special version of spin-Kalodge-Moser system. You know, that's, I want to distinguish the names of Hikami and Wadati, but there were many people who did various pieces of this. So the quantum Hamiltonians have this form. H1 is just sum over quantum momentums. H2 is the Laplacian plus the interaction. The interaction involves the permutations. So the space where they all act is this. It's the space of functions in Z1, Zn, tensor the tensor product of n capital dimensional spaces. And then we take the symmetric part of it, where the symmetric group acts diagonally on functions and on tensor products. This is all well known for the audience, I'm pretty sure about this. So now if we look at these Hamiltonians, you can see that here is the quantum correction, and here's the classical part, and here's also classical part as h goes to 0. And the same is everywhere. So all these Hamiltonians, they have the form h0 times the identity matrix plus h times some quantum things. So here is the list of classical and quantum things. So classically, the first one is sum of the momentums. The first m is 0. The first classical Hamiltonian is the usual classical Hamiltonian of Kalodjera-Moser system. Here we have the strange Hamiltonian, which is very familiar to everybody, or at least to most of the people in the audience. And then we have the third Hamiltonian, and so on. So what's nice about these things is that they satisfy these conditions. So if xt is a trajectory of classical spin, classical non-spin, usual Kalodjera-Moser system, so then I think I screwed up notations. Hmk is equal to exactly h1k. So then we have these identities, and so we have the kind of hybrid quantum system. So the theorem that I want to attribute to us, but many variations of this theorem were known, and maybe even this theorem is known. So I don't claim any priority here. But the fact is that the multi-time evolution for Kalodjera-Moser-Sutherland system has this fixed point when Q are equidistributed in the unit circle and P are 0. In fact, you know, if P are not 0, then there is a kind of motion on of these points, but that's a fixed point. That's unique fixed point. So because it's a fixed point, these equations, these ones, they give the commutativity of these operators, and M2 is exactly Haldane-Shastry operator. So the conclusion is that Haldane-Shastry operator is kind of a particular case of something that we can call dynamical Haldane-Shastry systems. And they live over Liouville tori of classical Kalodjera-Moser-Sutherland system. And so the situation is that there are n-dimensional tori that everyone knows about it. There is this fixed point x star. That's the zero-dimensional model, zero-dimensional orbit. But then it turns out that naturally between 0 and n, there is a whole spectrum. So for each k between 1 and n minus 1, there are certain types of degenerate Liouville tori of dimension k. So I didn't list here k equals 0 because it's already listed above. This is a fixed point, and k equals n. These are generic Liouville tori for which we have this Kolmogorov, Arnold Liouville theory. So there are n choose k types of this tori. They can be explicitly described. So and this Hamiltonians H1, which is the same as nk in the notation above, they give a flat connection on each Liouville torus, and they give some kind of non-stationary dynamics, probably very special and integrable in some sense. So the natural questions is, well, to study this non-stationary dynamics. And as in Haldane-Shastry model, of course, probably the most interesting thing is to consider the limit n goes to infinity, but not over maximal tori, but starting from tori of dimension 1, 2, 3, and so on. But n goes to infinity. So that's the kind of some ideas. So then related upcoming work I want to advertise, here we saw that the base of the Lagrangian vibration is stratified naturally in an interesting way. So similar stratification exists for classical spin color Moser systems. And then there are hybrid systems above this. There is a whole universe of hybrid dynamics that can be studied here. So I have to finish. Happy birthday, Philippe. My favorite thing is to make
thank you very much.
In the most important places.
Yes, if so, if
sorry,
there...
Philippe, it's not intentional. It's my dyslexia.
Okay, maybe there are questions. Let's see. Yes, just a second. Okay.
Can you hear me? Okay.
Yes.
I have two questions, if you allow me, please. In the very beginning of your talk, actually. So back to the first definitions, I was wondering. So your definition. So the thing that you say that the center of your algebra is trivial or just corresponds to is trivial in the fiber, and when you lift it, it's just the complexified functions. Is it an axiom or a result?
Which part of this?
The very beginning, actually, when you say that.
It's an axiom, yes.
It's an axiom.
So
okay.
what I want to construct is so not I want to construct, but what these hybrid quantum algebras of observables are. These are associative algebras, which are, in these simplest examples, they are finite dimensional over the center. And the center is the complexified algebra of observables over the phase space.
Okay, cool. Okay, thank you. And the next question would be about your definition of a representation of your Azumaya-Poisson algebra. In the definition, you enforced representations to be irreducible in the fiber. So I was wondering, why would you want that?
Simply because, in quantum mechanics, typically what do you have? You have the Heisenberg algebra as the algebra of observables. It has a trivial center and unique up to an isomorphism irreducible representation. So I was just mimicking this. But of course, in general, you can have, like if you will take quantum groups at roots of unity, the center, they are all finite dimensional over the center for simple finite dimensional algebras. But the center is a Poisson algebra. It's with non-trivial Poisson center, so there are syncretic leaves. And the fibers are not simple algebras, but semi-simple algebras of a generic point. And of course, they have some interesting and non-trivial representations. So this is all just tailored for quantum mechanics, where the main hero is Heisenberg algebra.
Okay, so it does. So what you just described doesn't apply to your setting, right? So it's.
Sorry.
So in your paper, what you describe only apply to the case when it's irreducible, right?
Yeah, but you can easily generalize it to irreducible. I mean, you see, in representation theory of quantum groups, there is a whole chapter, representation theory of quantum groups at roots of unity, which are Azumaya kind of type Hopf algebras. And there are many results about the structure of these representations and so on. So I'm not inventing anything new in this respect. It's just it's very generic. What is new is the integrable system.
Okay, cool. Thank you.
Yeah, there is another question.
Okay.
Yeah. Why don't you say your name? Yes.
Yeah, sorry. Hi, Kolja. This is Jules Lammers. Thanks for the nice talk. I have a question which is about Haldane Shastri. So one of the sort of surprising, I guess, or computational facts is that the wave functions are related to these Jack polynomials at the special zonal spherical point, which are also known to appear in harmonic analysis. And as far as I understand it, in Haldane Shastri, this is just kind of a computational fact, but not really conceptually. I don't know how it relates to harmonic analysis. So do you think that your point of view helps understand this?
I hope. I mean, I hope, because you see, there are no results about this. I want to emphasize, I hope. So the reason for this hope is that if you take the Haldane Shastri, not Haldane Shastri, Hikami-Wadati system, so then the eigenfunctions are known. I think there were papers by Uglov and other people where these eigenfunctions described in some terms of harmonic analysis. And so in some sense, all you have to do is you have to pass through the correct semi-classical limit.
But general Hikami-Wadati would have a kind of a coupling constant, right? So it's not at this fixed value of the coupling constant corresponding to this.
Yeah, you have to take the limit when the beta, the coupling constant for them, goes to infinity.
Right. Okay.
And
so the value
one
beta,
more important thing is that,
sorry, the value beta equals to 2 is a bit sort of a surprise from that point of view, right? You send beta to infinity and you get a system with eigenfunctions beta equals to 2.
I want to emphasize that the problem of computing eigenfunctions and eigenvalues you can pose only for operators or commuting system of commuting operators. So here, this is not a system of commuting operators. This is a flat connection over the Liouville torus. So the natural thing here is to find kind of flat sections, in other words, solutions to the non-stationary problem. It's not a spectral problem. It's a kind of, it becomes a non-stationary problem, but still it's a flat connection. So it's, I mean, it would be nice to find solutions to these differential equations.
All right, thanks.
It's like solving, you see, there is a Gaden problem where you find eigenvectors and eigenvalues. And then Gaden commuting Hamiltonians. And then there is Knizhnik-Zamolodchikov connection, where you have to solve differential equations. So these hybrid systems, they are more like Knizhnik-Zamolodchikov equations.
Sure, yeah.
Okay, thank you very much. Are there other questions? Okay, then we thank the speaker again.
Thank you again for the invitation. Philippe, happy birthday, and have a good conference.